Hi guys, we're going to be talking about one of those Physics 2 problems I gave you for homework. I think it's worth talking about just because Physics 2 is a little bit of a different animal. You'll see why as we go through a little bit. It's not hard by any means or harder by any means for sure, but it's more of a conceptual approach than a mathematical approach. So I thought it would be worth it to do a problem together. So this is an electrostatics problem. I'm sure you've gathered. And we are going to be looking at forces and energy of this charge configuration. So I'm going to go ahead and read the problem. The figure above represents four objects with charges as shown that are held in place at the corners of a square. Point P is at the center of the square, a distance d from each of the objects. Let me move that so you can see it. A distance d from each of the objects. Express all algebraic answers to the following in terms of q, d, and physical constants. So what they want us to do now is on the dot below, draw an arrow that represents the direction of the net electric force exerted on the object with a charge plus q by the other three objects. Okay. So let's just look at it from above and consider each of the smaller forces. So one thing that is tricky actually is they want you to draw, they're looking at the charge q, not the point P. I thought it was going to be point P when I first read this. So just be sure you read carefully because they're tricky in this a little bit. A lot of it is, careful reading. So let's look at the directions of the forces. So this force or charge over here is going to exert an upward force, right? And we'll give it 2 arrows long because it's charge 2q. And a distance 1 away. Actually, let's just kind of just eyeball it. So then this one is going to be a repulsive force of length 2, and because distance, well, I guess not 1 away, but 1 side length. They're defining d as this. Now this one is also a charge 2, and it's going to be an attractive because it's negative, but it's farther away, so it's actually going to be weaker than either of these. So let's kind of that's about right, I think. So now we have to figure out what the net direction is, right? So we have to add these two together. If you add these two together and get their vector sum, the resultant vector, it should be stronger than that one because both of the legs individually are bigger, and it's a right triangle, so the hypotenuse must be bigger. So the net force you feel is actually going to be that way. And I'm going to label it F just because they like to... Oh, you can't see my picture drawing. I forget that not all of my paper is on the screen. So the net force field is going to be that way. I'm going to label F just because, well, they like it when you label things. So calculate the magnitude of the electric field at point P due to all 4 objects. So now we're looking at electric field. So let's flip the page and finish reading the question. The dot below, draw an arrow to indicate the direction of the net field at point P. So here they want us to calculate the field. I'm going to do this on the other side because I like looking at that picture. So I'm going to flip it back. So I'm going to do my electric field here in red just to not confuse it with the force I did earlier. So this guy is repelling, so all of them are equidistant away. So I can actually consider the how long things are easily without having to worry about distances. So distant power 2, or not power 2, but charge 2, magnitude 2. This one's, and those are both repulsive, so this one causes this arrow, and this arrow is caused by this one. So now this guy's going to be an attractive force, so he's going to be just as strong as the other ones. And this guy is going to be a repulsive force, so it's going to be half as big as the other ones because it's got half the charge. So we can see that this and this one will cancel, and these two are going to add up. So I don't really have to worry about vector stuff because I know they're going to add up. All right. So calculating the electric field, I know that the field from this point up here and that one down there canceled, and these ones over here are going to add together, right? So the electric field I can just do in magnitude, right? Because I think it said magnitude. Yeah, it said magnitude, so I don't have to indicate direction at all. So I can say it's the electric field K from 2Q over D plus D squared, because electric field, plus K from Q over D squared. And I want to add them because they're both in the same direction. So this is just going to simply be electric field equals 3KQ over D squared. All right, part 2. I don't have a lot of space for this, but we're going to do it anyways. Calculate the electric potential at point P due to all 4 charges, or all 4 objects. So the nice thing about electric potential, as you guys know, is that it's a scalar, so I don't have to worry about directions anymore. I can just look at the total. So I know that there are 4 objects a distance d away, so it could have 4 terms. But I know that 2 of them are going to be identical. So I know that I'm going to get 2 times k 2q over d. I'm not squaring the bottom because it's potential. Minus, I'm going to subtract the negative one because, well, it's negative. And then I'm going to add the positive one, the positive single one. So it's going to be k q over d. And I can just add all those things up. So this is going to be, so this one cancels with that too. And so I end up with 3kq over d as my electric potential. All right, so lastly, we have part C. Now, part C is that big paragraph response question. And rather than watching me write it out, I'm just going to talk about it with you guys. So let's read the question first. In a coherent paragraph length response, so that they're specifying they want a paragraph length response from you, briefly describe the meaning of electric potential energy and explain qualitatively how electric potential energy can be related to work. Also explain qualitatively how the electric potential energy of the 4-object system would change if the plus q and plus 2q objects on the right side of the square now switch positions, as shown in the figure below. Support your explanation using appropriate physics principles. So when we do this one, I guess we should just start talking about it. So electric potential energy, since the potential energy, it's an energy stored, right? So it's the energy stored in the charge configuration. And there's the charge configuration that we have here. And one way to think about it is if you have a single, and to connect it to work, if you have a single point charge floating in space, it didn't take you any energy to get there. Getting you there, that one there was free. But when I bring in my second point charge, so let's just say I start with Q, because I like to start with single Q. When I bring in my second point charge, I get whatever the energy is associated with these two. Right? I can calculate the potential at this point and bring in a charge 2Q and then figure out the energy it would cost me. Right? And then I can do the same over here, but the potential is now going to be caused by these two. So that's going to have more energy get there. And then this one's actually going to give energy back because it's attracted. So the work I have to do bringing these charged particles in will be equal to the energy stored in my charge configuration. So now that if we want switch these two charges like they've already done, because before we had single Q up here. If we want to switch these two, it's going to cost us energy. And the reason for that is I've taken this big 2Q and put it closer to this other 2Q, but also moved it farther from this minus 2Q, which was pulling on it. So now it feels a weaker pull. So it costs us energy to put this one up here. And by the same token, bringing this one down here, it now has less, this one in particular, it has at a lower potential than it was before, because it's now, it's farther from this one. This one's the same distance, and it's closer to this negative one. So it's going to have, so overall you're lowering the energy of your system by switching those two. And I think that's all we need to talk about with it. Let's just look at the question again real quick to make sure. In a coherent paragraph response, briefly describe the meaning of electric potential energy and explain how qualitatively how electric potential energy can be related to work. I think we did that. Also explain qualitatively how the electric potential energy of the 4-object system would change if the plus Q and the plus 2Q objects on the right side of the square now switch positions as in the figure below. I think we did that. All right, so I'm going to call this one good, and hopefully this was helpful to you. See you in the next one.